Hey 13 DPs, welcome back. This is your quick fire topic 6 revision. So you guys did really well with this when we first learnt it last year. So very quickly, let's recap. Okay, so first of all, what is rate of a reaction? So there's two ways you can define it. It's either the increase in product concentration over time or decrease in reactant concentration over time. You need to know one of these definitions. It's quite a common question in your IB exam. So here's like a general one: the change in concentration of products or reactants with time. So you can see here, this is products increasing concentration over time or reactants decreasing, either which are always are equally common. Rate is always going to be a positive value because rate is what we are deducing here. Okay, so what do we notice about graphs? So first of all, rate graphs are curves, and the significance of that is the fact that the rate changes continuously over a reaction. And so if you look at this graph on the right, you've got a blue line and a purple line. Now, if we took the gradient of the blue line and compared that to the gradient of the B line, gradient is rise over run. And so if you did rise over run, you would end up finding out that the steeper line, which is gradient A, has a faster initial rate of reaction. Now, I say initial rate of reaction because the rate is continuously changing. You can see it's slowing here. And then here, they end up at the same point, which is when the reaction is finished. So we can only ever say that reactions have a faster initial rate of reaction because they always end up at the same point. So how do you calculate the gradient of a curve? So here's an example here. So you've got a curve. So to do a gradient, you need to draw a tangent, which is a straight line to the curve. And then you want to pick 2 points on your tangent that are quite far apart. The larger the values you can use, the better. Okay, so you do rise over run. So this one here, they've simply used the actual points. So they've done negative 2.4 over 283, and that gives you the rate. But that's only the rate at that point where it touches, okay? Because rate changes. It's not a linear thing. So that's the rate at that particular time. Okay, so because rate's not constant, if you wanted to know various rates of an experiment over time, you'd have to do multiple tangents. So see here, you can see multiple tangents to the line. So up here, we've got a rate of 2.9 times 10 to the negative 2, but down here, we've got a rate of negative 7.2 times 10 to the negative 3, and that was negative. Now, I initially said on that very first slide that you can't have a negative rate. They can only be positive. So what must I be referring to here? And that's the fact that this is doing the change in concentration over time, and the concentration is going down. So it's the concentration of reactants decreasing over time, which is why it's negative, not because the rate is actually negative. Okay, rate of reaction will always be largest at the start of a reaction. Why is that? At the beginning of the reaction, you have the most reactant particles available. That means there'll be the most collisions available at that point in time. And as the reaction proceeds, you'll have less and less reactant particles, which means there'll be less and less collisions, which is why the rate decreases. So as I was saying before, and I should have probably been a bit more specific as the slide's telling me to be, this is the gradient. The gradient's negative, but the rate is actually positive. I did kind of represent that. That's purely because we're talking about changing the concentration, and this is decreasing reactant concentration over time, but the rate will still be positive. Okay. So which experiment shows the fastest rate of reaction, and what's wrong with this question? This question should be which shows the fastest initial rate of reaction, and the answer would be A, and that's purely because it has, if we did a tangent to the line, it would be much steeper than that of B, indicating a faster rate of reaction initially. How do we measure rate of reaction? So there's actually quite a few methods. So, and you guys will have done a lot of this over your time in chemistry. So the first one, I'm actually just going to run through these, is gas production. Now you can use a gas syringe. Unfortunately, our gas syringes at school don't have a very small scale, so that can be quite annoying to actually do experiments with. It's okay for kind of slapdash experiments where we just need a broad range, but unfortunately they were no good for the IAs, if you remember this year. But anyway, you can connect them up with a delivery tube, and as gas is produced, it'll push that valve outwards and you can measure how much gas is produced. Another way is water displacement. Now this picture here uses a burette upside down, but a measuring cylinder works perfectly well. You have to start the experiment by fully submerging whatever this vessel is. So there's no air pockets and you can read off the first value. And then once the reaction produced, what happens is the gas pushes the water out, so displaces the water, and you can measure the difference between the initial and where you end up, and that's the amount of gas produced. So that's quite cool. Yeah, so you've just got to make sure for this one here that the gas that you're producing isn't water soluble, or else if it's water soluble, this won't work. Okay, so mass changes. So if you were to put some calcium carbonate with some HCl on a mass balance, over time that mass would decrease, and the reason why is because the products of this reaction are calcium chloride, CO2 and H2O, and we know that this is a gas and the gas will escape, and so therefore the mass will go down. This doesn't work well when you're trying to do something like H2, and that's purely because H2's got such a small mass that you won't see much of a difference. So mass change over time. So this is just a graph to show you here that you could actually graph mass, or graph whatever, mass over time. Yeah, and you could take the gradient if you wanted to, and that would give you a point at that. But yeah, that's just to show you can. Oh, okay, changing color transmission. Lots of you did colorimetry for your IAs. I think it's wonderful. So let's talk a little bit about what colorimetry does. So colorimetry absorbs the amount of light going through a sample, and then compares that to the initial light source. So we can see how much a sample absorbs and how much is transmitted. So this is me just explaining that. So here's a picture to kind of show you. So here's a solution, okay? So white light gets shone through a sample. The sample will actually, well, first of all, there's a wavelength selector, okay? Here, now that wavelength selector is going to limit some of the light that goes in, because we want it to produce a maximum absorption. And then what we can do is we can see how much is absorbed by the sample and how much gets detected back here. Okay, so we always want to select a wavelength where you're going to see the maximum absorbance in your sample. Yeah, and so you can compare that and work out the absorbance. So we actually measure absorbance on our little devices at school, and so we can actually see or compare coloured solutions by seeing how much they absorb light. Okay, so yeah. So Beer's law, so this concept, there's a nice graph I think. So Beer's law, you can do absorbance over concentration. To make Beer's law work, you have to do a standard curve to start. A standard curve means using concentrations that you actually know. So let's say we were trying to measure copper sulfate concentration using Beer's law. We would first make up some copper sulfate of about 0.5 mole per litre and then decrease the concentration from there. So you'd have about, this could be 0.5, and then you could do 0.4 and 0.3 and 0.2. You can't really go much higher. You can go up to 1 mole, but it is hard to kind of get copper sulfate dissolving and you have to use a lot of it. So anyway, you do your standard curve, and a standard curve absorbance is directly related to concentration. So therefore you would see this straight line of absorbance, hopefully, if you've made your concentrations really nicely. And so what we can do there is, if we've got this standard curve of copper sulfate using concentrations that we know, if we then had a sample that had some copper in it and we didn't know its concentration, what you could do is measure the absorbance, and then once you get that value, you could then come across, go down and be like, huzzah, that's the concentration. And so that's how Beer's law works. Hopefully that makes sense. Yeah. Okay, so what about changing concentration? So you can actually use concentration to measure how reactions are proceeding, and we can do this doing titrations, where you withdraw some of the sample at regular intervals and do a titration with them. This one's quite time consuming, but it is still possible. Another one is conductivity. So for conductivity, you need free moving charged particles, so there has to be a change in that. And anyway, yeah, you can compare how a reaction's going by the number of charged particles. So this one here, for instance, you've got 12 ions going to 0, so the conductivity would decrease as this reaction proceeds. So the last method is non-continuous methods, and this is when you arbitrarily pick an end point to your experiment because it's too hard to determine otherwise. So an example you probably know from year 11 is when you put an X on a bit of paper and you did your experiment on a conical flask above it. Geez, that's a terrible flask. And when you could no longer see the X, you stopped your timer. So that's a good one. You could also do when you add a piece of magnesium to HCl and you add a few drops of detergent, you could have a line on your test tube where you measure when the bubbles get to that line and you press stop. So that's like a method where you see how long it takes for bubbles to reach a certain mark. If you were doing something with diffusion, you could put 2 dots on a piece of paper and see how long it takes for the color to diffuse between 2 dots, that sort of thing. So it's when you arbitrarily pick an end point. Okay, I'm going to pause here and we'll come back to collision theory as part B of this video. Hopefully that's explained everything so far. If you've got any questions, please let me know on Teams.